Thank you very much. Thank you very much. There's a question there.
For the simulations of the tidal wave galaxies, they assume alternative gravity or Newtonian gravity?
That's a very good question. All of that was done in Newtonian dynamics because we don't actually have a code to do that in an alternative gravity framework. I'd love to do these calculations with a non-Newtonian code, but that code has to first be developed to suit those needs. And working in MOND is numerically much more difficult because the external, so the boundary conditions are so much more difficult to handle. So we need expert people to develop these codes and then do these simulations. The reason why it works with Newton is, first of all, Newton is pretty good. You know, it's very close to the truth, but it seems that the external field effect might be kicking in here. So in MOND, if you have a substantial external field, it actually suppresses the MOND effect and the objects start looking like Newtonian objects. So this might be a reason why the Newtonian simulations seem to work fairly well. I wouldn't say we get it spot on, but it's pretty good.
There's a question over there.
Could you explain a little bit more how you think MOND might actually match that data?
Well, I'm certainly not the correct person to ask that in detail, but from being in touch with Gary Angus, who has looked at this, who's actually done these calculations, it seems that the MOND effect, non-Newtonian effects or non-Einsteinian effects would not actually be very relevant in the very early universe where you have very high densities. And so you're still nearly in the standard framework, except that you then do need dark matter, as correctly pointed out by Simon White. And the interesting result by Gary Angus actually is, and this is published work, is that in order to fit the current WMAP data, you need to invoke 11 electron-volt stellar neutrinos. And you can then ask the question, is that hypothesis in MOND consistent with, say, galaxy clusters? Because you'd have to, because in MOND you also need dark matter in galaxy clusters. You need far less, but you still need some. And they've looked at this Tremaine-Gunn phase space limit, and Gary Angus finds that indeed it's beautifully consistent for many galaxy clusters. You get the same result as for the WMAP result. So there's again a consistency argument which doesn't prove the theory or that approach, but it gives a suggestion that there is definitely there's a non-unique solution to the galaxy clusters or large-scale structure essentially and WMAP results. So it's not only lambda CDM, but other approaches would also be working.
Simon?
Yes, I'd like to comment on that particular point, which will come back later, but since it came up now, it's useful. I think, as you showed, Gary's model is a beautiful fit to the WMAP data. That is because it is, in fact, the same model the WMAP people fit. It has the same Hubble constant, the same geometry, the same baryon density, and the same density, 22% of dark matter in a new elementary particle not yet seen on the Earth. So in fact, it is exactly the same model. The only difference is in the identification of what the dark matter particle is. So that is the standard model, except for the nature of the particle. And the reason it evolves to the same thing is because if you start from those initial conditions, it will evolve and produce clusters in exactly the same way. So that model fits, but does not need MOND.
Except if I could, can I?
Yeah.
So because if you are then saying that you have 11 electron-volt stellar neutrinos, then later on you do need MOND to expand the galaxies, right? So in that sense, one does need MOND. And also the galaxy clusters, of course, you require non-Newtonian dynamics.
No, the galaxy clusters are okay. The galaxies, I agree.
Okay, that seems...
You didn't say anything about the bullet cluster, which I thought is usually touted as being very difficult for MOND to...
That is a wrong statement, actually, because if you are again in this framework with 11 electron-volt stellar neutrinos, which might actually be found in Karlsruhe within some years, possibly, then the bullet cluster is perfectly okay. I mean, whatever you do in Mond, you do need dark matter, and the dark matter would behave just like is evident in the images. So it separates away from the gas, follows the galaxies, and there's no issue. In fact, the problem with the bullet cluster, as stated by those people who've looked at this problem, is that it is inconsistent with lambda CDM. So I don't know if Simon will comment on that, but probably you will. But the problem with the bullet cluster is that this is work by Gary Burkhardt and some other people. You require in lambda CDM a certain velocity of the two. It's about, to get that morphology. That velocity is extremely high. It's about 3,000 kilometers per second. And apparently this velocity is not obtainable, at least not easily obtainable in lambda CDM, right? So it's actually a counter-argument. It actually disproves lambda CDM. However, if you're in a Mondian framework, you get those sort of velocities naturally. So the bullet cluster, in fact, can be interpreted to be a major problem for lambda CDM and a perfect agreement with Mond plus the hot dark matter. And there's another cluster which is called the train wreck cluster, which usually people don't talk about, and that seems to be a major problem for lambda CDM.
Good. It seems that all the urgent questions have been asked, so I guess we close here again. Thank Pavel again.